So we'll now continue on with, we saw basically what are variables, we saw constants, and we saw the basic structure of a program, and we saw how to do basic print and scan, which is to read and write. One thing that I forgot to mention is, in some, as I said, right, the printf and scanf functions are typically implemented with a lot of the operating system support. Like when you do in a general purpose computer, printf is using the OS services to get the printer. Scanf uses the same way the keyboard interface, the drivers to get the data inside. On some embedded systems, you may not use the standard printf and scanf, but there will be typically functions provided by a library which is built for that embedded board. For example, you may have a small LCD panel on that. Just as an example, you may have a single line panel on that embedded system, very small embedded system. So if you want to print something on it, they will give you special functions to do that, or they may call it by a different name. But typically, you'll have to read the data, the manual for that IDE, for the target board, whatever software environment you're using, right? They will give you specific functions by which you can actually put some output or read some input. So there will be some mechanism, but they may not exactly follow the printf scanner, but it's good to still understand printf scanner because many environments support it. And as a C language, you can understand how it is done. But embedded platforms sometimes may not give the same name or the same format specifiers, but there will be some way to do it. But the concept, if you understand, I'm sure you'll be able to read. So you have to study the software environment that you're going to use on the platform and choose that appropriately. Okay. Now moving on, as in any computer system, the reason we use a computer or a microcontroller is do some processing, right? We want to manipulate the data, do some computations. So one of the first things that you try to do is what are called arithmetic operations, which are like your typical addition, subtraction, multiplication, division. So these are standard, like whatever you understand, right? If you want to multiply two numbers, I use the multiplication operator. If you want to add two numbers, I use the addition operator. And if you want to do subtraction, division, and so on, and there's something called as a modulo operator, which gives you the remainder. Okay, these are standard operators, and they have precedence, plus or minus are the same precedence, but it's low, something called operator precedence. Will come to quickly how to interpret that. And there's also something called unary minus sign, which, for example, to treat a negative number, just put one minus sign before a variable name, it means the negative of that. And there's something called associativity, which is like if all are of the same priority, where does it work? The operation goes from left to right. That's called associativity, actually. Okay. Now, take some simple examples. You can, if I have say two variables, how do you write some statements using arithmetic operators, right? Suppose say let's say I have two integer variables x comma y. Okay, I've initialized x equal to 5, and I want to add some value to that and store it into y. I can say x plus 10. Okay? This is a very valid, this is a usage of this operator plus, right? Or if I say y is equal to minus x. So this is called as a unary negative operator, which means take the x, negate it, which is minus 5, and store it into y. So similarly, subtraction, all that happens in the same way, right? I can just say x minus 5 or whatever. So that happens. Multiplication is star. So pretty much simple, and you can have in a single expression, you can have multiple of them. I can just say x plus 10. I can just say star 2. This is also valid. And in an expression like this, if you put these parentheses, it kind of groups them together. So this is done first, and this value totally is used to multiply with 2. Okay. So this, if you have anytime you have any confusion about operator precedence, right, which happens first? For example, if I written this as x plus 10 star 2, you have to then remember the precedence rules, whether this is done first and that result is multiplied with 2, or is this done first and that is added to x. It so happens in this case, the multiplication has a higher precedence, so 10 into 2 will be done first, then 20 plus x, that result will be stored in y. Whereas I don't want that. I want x plus 10 to be done, that to be multiplied by 2. Then I can put this to ensure the order is. So it's always a good practice to use them when you are in doubt. And for the reader of the code also, it is very clear. Even if I don't remember the operator precedence table, I can follow the code without too much of confusion. It's always a good programming practice. Even if you remember the precedence rules, it's good to put them to ensure it's very clear what you're trying to do. Okay. So these are examples of arithmetic operators. And the modulo operator is a remainder operator. Okay, what is a modulo? Suppose say I have a number, say let's take x equal to 102, right? And I have another value y. If I say x modulo 10, right? So the remainder will get stored into y. So if I divide x by 10, 102 by 10, what is the remainder? 2, right? So y will get the value, y will actually have the value 2. Is that clear? That's what is called as a modulo operator. Then another group of operators are called the relational operators. Okay, So what are the relational operators? Relational operators are used to compare two values, okay, and the return value, like essentially you get either a true or a false, and in C, if you use them in an expression to store that result in a value, you will either get a 0 or a 1. So let's take an example. So what are the relational operators? I'll show you some examples. Relational operators are like greater than, less than, greater than or equal to, less than or equal to, then equal to equal. Two equal to's together is to check for equality, and this not equal, this exclamation mark is say not equal to, and you can say all the greater than, lesser than have the same precedence, equal to and have lower precedence than this, and generally they have lower precedence than arithmetic operators. Okay, that's the order. Now let's take some example. Let's go to the compiler and then probably take a few examples so that the relational operator concepts becomes clearer. Okay, let's take, and I also want to demonstrate what really gets stored when I have some numbers, right? Okay, let's take this example. Let's declare some two other variables. For example, if I write a statement like m is equal to x less than y, okay, and print what is stored in m. Okay. Now in this case, all of you can see the screen, right? Able to see the screen. Okay. Now in this case, what am I writing? The relational expression is saying x less than y. What is the value of x? X has a value 2, y has a value 31. X less than y, is it true? True or false? Is 2 less than 31? True, right? So when it is a true, the value 1 will get, the result of that expression, right? X less than will be 1. And that 1 will get stored in m. Let's see whether it's behaving as expected. Let's run the program. You can see m is equal to 1. Suppose I created a false thing. Suppose instead of, if I say x is greater than y, right? This is false. So if it is false, this will evaluate to false. In the case of false, in a relation expression, if you're trying to store a value, it will store the value 0. Is that clear? One thing to remember is in C, 0 is false. Any non-zero value is generally considered true. Suppose we'll see later things like if, check, and all that. If you are checking some variable for truth or false, any non-zero will be considered as a true value. Whereas in a relational expression, when the result of a relational expression will evaluate to a 0 or a 1. 0 means false, 1 means true. But in general, in C, 0 is false. Anything other than 0 is considered true. When we compare later, you will see that experience. So this is an example of how you can do that. Like similarly, you can compare equal to also. For example, if I say x equal to y, right? That is also false, isn't it? X equal to 5 is also false. Suppose I say x equal to say 2. X is, I have given the value 2. If I compare it with 2, it should be 1. Can you see it is 1 here? Is that clear? So how you can use relational expressions? The result of a relational expression either is 0 or a 1. And now next step we will see how we can use one more class of operators and we can combine these two. Let's look at that next one. So we saw relational operators. So we saw these examples also, right? So I told you, we demonstrated just now. If I say z equal to x greater than y, 4 is greater than 2. So z will get the value 1, which is indicating value 1 means which is true, right? That's why you will get a value 1 in this case. Suppose I say x less than y, x is 4, 4 less than 2, it's false, 4 is not less than 2. So z will now get the value 0, right? That's what we just saw in the online demonstration also. So these are relational operators and simple examples for that. The next step is called logical operators. Suppose in any programming, right, you may want to check multiple conditions, right? You may want to take actions, even a general everyday programming, you may want to take multiple actions, right? We saw that example of the sum. I want to check whether the sum above is empty. I mean, which means there is space for water to go. And the sum below, the underground sum has water. So only when both these conditions are true, I want to take some action, which means I'm checking one thing, I'm getting some result, and one more condition. So in many cases, we'll always want to have multiple checks. Even in everyday examples, right? I may want to check like, I didn't have breakfast in the morning and I am hungry now, I will eat, right? If I'm not hungry, I won't eat. If I had already had breakfast, I don't want to eat. So there is always in any programming, you'll always see scenarios where you always do some logical comparisons using and, or, not, and so on, right? So you have three operators, which is called a logical AND operator, which is denoted by two ampersand symbols together. Then you have a logical OR. You have these two pipe characters, a vertical line, which is called as a pipe character. This is called as a pipe character. Two pipe characters together is called a logical OR. And this exclamation mark is called as a logical NOT. Logical NOT, true will become false, false will become true. Basically, that's what is a logical NOT, right? And how does it work? If I have, say, expression 1, logical AND expression 2, the result will be true only when both are true. It's just common sense, like how just like English, right? This and that, okay? Similarly, or is this or. If any expression 1 is true or expression 2 is true, this result will be true. Is that clear? So that's how a logical operator works. And you can combine relational and logical, right? We saw relational operators can give you true or false, either 0 or 1, and you can combine them to have complex expressions, just like the example here, right? We have three variables, x equal to y, y equal to 2, z equal to 10. I'm saying x greater than y and z greater than y. Now x is 4, y is 2. So x greater than 5, it is true, so it will get a value 1, for example here. Z is 10, y is 2, so this is also 1. So this is true and this is true, so the total expression is true. Is that clear? How that works? So that's why res will now, the variable res will get the value 1. Whereas you see here, x is less than y. Is that true? X less than y, it's not true, it is false, so it will be 0. And z greater than y. Z is actually 10, 10 greater than y, this is true. So the total result will be false. Actually, C, one thing you have to remember, is actually a very important thing in relational logical expressions. In C language, there is an optimization built in. If you see a statement like this, and the expression evaluation happens from the left to the right, right? X less than y was false, right? And then the next operation is a logical AND. Now, the moment one parameter to that operator is false, we know the operation is going to be false. So actually C will optimize out, it won't even evaluate this, which is important if you are using some side effects here. For example, we will see some examples later. Suppose there can be a function call here also. Sometimes we may do that. If this was false, this function will not even get called. So it's important to remember in C, if you're evaluating a logical expression like this, the expression evaluation will stop the moment the result can be determined. So in this case, since it's a logical AND, the moment the first operation is false, irrespective of even if you have 4 more things there, even if all of them are true, the total result is going to be false because it's and whatever, right? So if one of them is false, I know the entire thing is false. So the remaining things will not even get executed. So this is important because sometimes you have something called increment operators, decrement operators. You may use it in expressions. Those operations will not even happen. So in C, you have to remember that if you're having some things here which have a side effect, side effects can be like increment, decrement operators, function calls. Those things, will not even happen if you are processing a statement like this. So it's important to remember that in C, there is a built-in optimization. The result will be, the expression evaluation will stop the moment the result is known. Similarly, if this was an OR operator, right? And the first one, expression 1 here, evaluated to true. Rest of it need not be evaluated because the moment it's an OR here, irrespective of it is a 0 or a 1, the result is going to be a true. Okay, that's important, something, a small point, but it's good to remember that because sometimes you get into situations where you can't debug that here. So here is an example of a OR statement, x less than y, it is false because 4 is not less than y, but z greater than y is true, so the entire result of this expression is true. Is that clear? So if you want to see some examples running here, we can just do the same thing on our online tool. So let's say we had this example, right? We can do something like this. M equal to, let us say, x less than y, and let's say y greater than z. Okay. In our case, x is less than y, which is true. Okay. X is less than y because 2 is less than 31. Y is greater than z, 31 is greater than 5. So the result of this entire thing should be true. If it is true, m should get the value 1. Can you see m is getting the value 1? Suppose I change one condition here. I say y is less than z. Okay. If y is less than z, this is going to be false. So true and false, right? So it's going to be false. So m should get the value 0 now. Getting the value, m is getting the value 0. So though you combine logical and relational expressions and build complicated evaluations as needed actually. Okay. Let's go back now. We saw arithmetic, we saw relational, we saw logical, and how to combine relational and logical together. Now we'll come to this important operator in C, which is called the increment and decrement operator. And there are two variants here, which are called prefix and postfix. We'll see what it is. So the increment operator is called plus plus. That's how you write an increment operator. And minus minus is called the decrement operator. Okay. How do you use it? You can see here. There are two ways to use it. Let's assume we have declared a variable x equal to 5 and some variable y we have uninitialized it, not initialized it. The moment you write a statement like this, say plus x, right? The value of x gets incremented. So plus x can be also seen as x equal to x plus 1. If I write a statement like this, the current value of x is taken, 1 is added, and the result is stored in x. Instead of writing like this, I can just say plus x. I can also write x plus plus. In both these cases, the value of x will be incremented by 1. There's only one difference. I'll come to the difference shortly. In both the cases, the value of x is going to be incremented. The difference is, if this is part of an expression, what value is taken for the overall expression is different. Let's take an example. I'll probably open a page and show you. So this is called increment. If I say minus minus x or x minus minus, in both cases, the value of x will get decremented. So that's called decrement operator. Okay. Now, the difference between putting it before x or after x comes into expression evaluation. Let's take a example. I mean, I'll show it to you in terms of how it happens, and then we'll see a example running. Okay. Let's take some values. Let's take int x equal to 5, y equal to 6, and then say z maybe z equal to 1, and let's take some another variable, say int m comma n or something like this, right? Okay. Suppose I write a statement m is equal to, I write something like this to be clear. This plus x plus y. This is one statement I'm writing. I can say n is equal to x plus y. Okay. So the difference between these two things is pre-increment, right? So this is an expression. For this expression, lost it. Okay. That's this. It's kind of once I'll redo it. So we had three variables. I'll do it again. Int x equal to 5, y is equal to 6. Is that something? Two variables, int m and n. I can write m is equal to plus x plus 6. This is one possibility. Or I can write n is equal to x plus 6. Okay. See, in either of the cases, after either this or this, let's see. In this case, when I put this prefix operation, for this expression evaluation, the value of x after the increment will be taken. So if say initially the value of x is 5, right? So plus x will make x to become 6. So that new value will be taken for this computation. So m will get the value 12. Okay. Instead of this, if I had written this, what will happen is, this is postfix. Now, or post increment we call it. So this x will be, original value will be taken. Original value of x is 5. So 5 plus 6, 11. So n will actually get the value 11. But in either case, x would have been modified. After this statement, if I print x equal to %d x, x in both the cases will have, this will always print 6. But what is taken for the expression evaluation is the only thing which is different between these two signs. Okay, is that clear? Maybe we'll run this code and show so that it's more clearer. This is a common point of confusion, how this postfix and prefix works. I'll just quickly show you some example snippet. Let's take the same example. Let's have the same numbers. Let's write two statements. We'll first write m is equal to, I'm just writing this so that, putting brackets so that everything is very clear. And let's print it here. Okay, now let's run this. Now what am I doing? Plus x plus y. So what should we expect to get? X is initially 2. Plus x will be 3. X will also get modified. Let's also print x, okay, so that you see how x is changing. X will always change. Okay. So 3 plus 31. So m should actually print 34 in this case, right? Can you see m is actually 34? X anyway has changed. X has become 3. Is that clear? Instead, if I had put this plus after x, right? What should happen here? X will get modified. X will still become 3. But for this expression, the value of x that would be taken is 2. Okay. So it will be 2 plus 31. It should print 33 here. Let's see whether it's working as expected. You see, x is now, m is actually 30. Is the difference clear? Between pre-increment and post-increment, that's the difference. Same thing, if you had done minus also, the same thing would have happened. If I, instead of plus, if I say minus, so 2 plus 31, it will still be 33. Okay, but if I had put this minus before x, right, it would have become 1 plus 31, it should have become 32. See that m is 32. Is that clear? The difference between post and pre. That's an important difference to understand actually. Then there is an interesting operator in C called the ternary operator. So it is actually very useful when you want to write in a single statement, check a condition and take two different types of actions. Okay. So the syntax is something like this. It's quite simple once you understand. It may look complicated initially, but nothing to worry. So the syntax is something like this. So some expression 1, it could be any expression, question mark, then expression 2, colon, expression 3. So what happens is expression 1 is first evaluated. If the expression 1 is true, then expression 2 is evaluated. Else, expression 3 is evaluated. That's the logic. Okay, it's almost like an if-else statement kind of construct. And typically we use it to, it's very most commonly used to initialize a variable with two different values given by expression 2 or expression 3 based on some condition. Okay, so it's a simple example is like this here. For example, we have taken two variables a and b, and I want to actually check what is the minimum. I want to find the minimum of these two variables and store it in this value called min. An easy way to write this is something like this. You can say expression 1 is this relational check a less than b. Okay, if a less than b is true, what I do, expression 2 is nothing but just a, expression 3 is nothing but b. So what happens, this expression, first expression 1 will be evaluated, a less than b, true, so only expression 2 will get evaluated. Expression 2 is nothing but it's the simplest form of an expression is a variable name. It's nothing but the value of the variable. Okay, so we call it an expression. The trivialist form of an expression is just giving a constant or variable name. Just a variable name a means the value of a that will get assigned to min. If a was not less than b, this would have been false, and then b will get evaluated. Nothing but the value of b will go there. So automatically what is happening here, this is actually implementing the logic of finding the minimum of a and b, and that value is getting stored in min. So if a was lesser than b, the value of a goes to b, goes to min. If the other way around, the value of b would have gone to min. Is that clear? So it's one way to use ternary operator, commonly used for things like this. So it's a very compact way. Instead of writing a big if loop, you can write this logic in a simple and compact fashion. So if you want to try that, try running it on this compiler, it's quickly we can do that. So let's write the same thing here. I say min is equal to x. I'll compare x and say y. Okay, and whatever is the minimum, I want to store it into min, and I'm just going to print min here. Okay, same code what we saw in the example. So I'm comparing x and y, and the lower of the two values will get assigned to min. In this case, we expect min to now get 2. Okay, min is getting 2. If, for example, if I had made y as a minus 2 or minus 3, it should actually get minus. You see, min has become minus 4. Is it seeing the logic? How to use this actually? That's all. Generally, it looks complicated, but once you understand that, it is pretty easy to understand. Now we'll move on to something which is quite important for embedded programmers, which are the bitwise operators. Okay, so we saw already the logical and we saw the logical are important for embedded programmers, which are the bitwise operators. Okay, so we saw already the logical and we saw the logical are, we saw the logical not. Those compare just two logical conditions, this condition and that condition, right? So that is where we put the two double ampersand symbol for logical and single two vertical characters for logical or and so on, right? Now we move on to bitwise operators. So bitwise operators operate on the individual bits of a variable, right? So this is where, we talked initially, we had that overview about how numbers are stored and all that, right? So inside the computer, everything is stored as a binary quantity. So that is how it's a number or a text or anything finally gets stored as a number. So you can take two variables. I mean, it's stored as a binary quantity. If you have a variable, another variable, you can take those two variables and you can do binary bitwise operations on them, right? So the bitwise operators in C allows you to treat the quantity stored as binary digits, and you can do logical, bitwise and bitwise or a bitwise XOR. So all that is possible in C. So the truth tables are given here. You can see the truth tables. Very simple. It's very straightforward. So logical AND, if both the bits are 0, the result is a 0. If even if one bit is 0, the result is still 0. The result is a 1 only when both the bits are 1. Okay, the truth table for AND operation. Or if one of the bit is 1, you will get the result as 1. So you have ones for either bit is 1, you get a 1. XOR means exclusive OR. So the result is a 1 only when one of the bits is a 1. So either A is 1 or B is 1, the result is a 1. If both are 0 or both are 1s, you will see the result is a 0. Not is a flipping. If it is a 0, it becomes a 1. If it is a 1, it becomes a 0. Is that clear? So these are bitwise operations, and these are very useful in embedded systems because we will use it often to extract things. We'll now see some examples of how we do it. I hope this truth table is clear, and or XOR and not. We'll now quickly see some examples of how we use it. Okay, so we'll just see the slide and then we'll actually go to the online tool and see things there. So the reason I'm using hexadecimal examples here is we know binary bit pattern and hexadecimal are easy to match, right? It's a one-to-one, you can quickly convert. For example, if I say 0x5555 unsigned short, so it's a 16-bit quantity. So in hexadecimal number, each symbol is 4 bits, right? Because 0 to 15, 4 bits. So 1, 2, 3, 4, it's a 16-bit quantity I'm trying to store into this value called x, variable called x. And what is 5? 5 is nothing. You can expand it quickly and write it, right? 5 is 0, 1, 0, 1. This is the other 5, 5, 5. Similarly, here I have stored A5, A5. A is 1, 0, 1, 0 is A. 0, 1, 0, 1 is 5. Again, another A5. So A and 5. Is that clear? How this is mapping? A5, A5 is this in binary, right? Then unsigned short is that. Now I am doing this operation x. This is stands for bitwise and x and y. Okay. Now we have these two things here. You can logically see what is going to be the result. Right? So the way it operates is it operates on individual bits in the same location. Okay. Assume say this is bit 0, this is bit 15, okay, this is bit 7, this is bit 8 and so on. Similarly for this, so x and y we are having it here. So what is going to be the result when you do x and y? You can take bit 0 of x, bit 0 of y, 1 and a 1. What is the result? It should be 1, right? 1 bitwise and, so you get a 1 here. 0 and a 0, you get a 0 here. Okay. 1 and a 1, you get a 1 here. 0 and a 0, you get a 0 here. Then you move on to this upper nibble here. 1 and a 0. 1 and 0 is what? 0. So that's why you got a 0 here. 0 and a 1, 0. 1 and a 0, 0. 0 and a 1, 0. So this nibble is all becoming 0. So then you come to the upper byte. 1 and 1, 1. 0, 0, 0. 1, 1, 1. 0 and a 0, 0. So you come till here. Then we are coming to the uppermost nibble. So 1 ampersand 0, it is 0. 0 ampersand 1, which is bitwise and is 0. So it's all becoming 0. So you can see quickly, if you write 5, 5, 5, 5. I took this example so it's easy to understand, right? It's if you look at the bit patterns between 5 and A, they are complementary. Because 5 is 0, 1, 0, 1 and A is 1, 0, 1, 0. So if you do a bitwise and of 5 and A in hexadecimal, you will get all zeros because it's a 1, it becomes a 0 here. Whereas 5 or with 5, you will get a 5. So you'll get 0, 1, 0, 1. This is again 0, this is 5. So that's why the result of x ampersand y is what? 0, 5, 0, 5, which is what we got here, right? 0, 5, 0. Is that clear? So if I did an R, you will see when you did a 5 and a when you do an R, right? You will get an F because 0, 1, 0, 1, 1, 0, 1, 0. So if you do a logical OR, what happens? 1, I mean, sorry, not logical OR, so bitwise OR, sorry. 1 bitwise OR with 0 is 1, 0 bitwise OR with 1 is 1, again a 1 and a 1, which is nothing but F. Okay, so you will get F, and then 5 OR with 5, you'll get the same value because OR it with itself, you'll get the same. So you get this value F5. Is that clear? Similarly, when you do exclusive OR, you will see when you do an exclusive OR also, you will have to make sure that the symbols don't match. So in this case, 1, 0, 0 exclusive OR is 1 is 1. 1 exclusive OR with 0 is 1. So you'll get F here. But whereas when you do exclusive OR of 5 with 5, right? In fact, that's a common property which is used in many microprocessors. If you want to quickly get a 0, you XOR a register with itself, right? You'll get a 0. Okay, so if I take 0, 1, 0, 1 and XOR with itself, right? 5 XOR with 5. That's what happens in the second nibble. So 1 exclusive OR with 1 will be 0. 0 with 0 will be 0. 1 with 1 will be 0. Will be 0. So that's why in this case the result becomes F0, F0. Okay. So if you reverse, for example, if I do reverse 5, 5, 5, 5, if I do not, 1s will become 0, 0 will become A. You can just check this out. Is that clear how we can do bitwise operations? We'll just probably run this and show it to you in code. So this is something very, very important for embedded programmers because we'll keep using it very often. This example, take the same example so it's easier. So I'm using unsigned short so that it's, I mean, it's very clear. We are just dealing with bit properties here. We are not worried about anything else. And printing also, I will use exclusive or, I mean, sorry, hexadecimal notation so that it becomes easy for us to understand what is getting printed. Okay, so let's try running this. So x 5 and a 5, right? If you do bitwise and it will stay as a 5. That's why you're getting a 5 here. Whereas 5 and a, you try it out because it is 0, 1, 0, 1 and 1, 0, 1, 0. It becomes 0. So that's why you get a 0 here. So you got a result. This leading 0 is missing. It's just printing it as 505. It is 0505. Is that clear? So instead, if I had put an R symbol, bitwise R here, bitwise R is this pipe character which is above the backslash. So this is the character for bitwise R. If I do this, let's see what's the result. You can see 5 R with 5 will become just 5. Nothing will change. Whereas 5 R with A, right, it will become F. Because wherever there's a 0, it's a 1 here, 1 is a 0. So it all becomes all ones. So you get F5, F5. Okay. Exclusive OR. The exclusive OR symbol is this, we call it caret, above the number 6, right? Above the number 6, that symbol which you see, that is called exclusive OR. Let's see what happens for that. Can you see what happens? Because 5 exclusive OR with 5 is 0. But 5 exclusive OR with A will again get F. So you're getting F0, F0. Is that clear? Now if I try the NOT operator, if I just say X is NOT operator is above, this is the NOT operator. So all the 5s became A's here. The NOT operator is above this, just left of the one number with a shift you have to use. That is a binary bitwise NOT operator. Is that clear how bitwise operations work? It's very, very important because in embedded systems, we will keep seeing this. Why it is very important is because using these operators, you can do things called masking. So let's take an example. For example, I have unsigned, let's say unsigned int. I have some register, some value like this, right? Let's assume in this register, okay, third bit is what I'm interested in. That is a flag which tells me whether data is available or not. Okay, maybe I can just illustrate here. I'm just blowing up that last F alone, right? Okay, that last F is 1111. Okay, in that I'm interested in this one bit or when I say third bit, I mean bit 2. And conventionally, we always start from bit 0, bit 1, bit 2. This bit I want to check and see whether it is 1 or a 0. Okay, so what I can do is I can create another pattern with a value bit position, only that bit position having a 1, and I can do a bitwise AND. Okay, so the pattern the pattern we generally call it as a mask. I mean, the conventionally we just call it as a mask. I'll just say int m equal to. So I want to create a pattern with 1 only here. So basically, I want to have all zeros leading all zeros. The last nibble alone I'm writing. The last nibble is, I'm not writing everything. Last nibble is 0, 1, 0, 0. I'm writing it in binary, okay? 0, 1, 0, 0, if I convert it into decimal or in hexadecimal, what will it be? 4. Are you clear? 0, 1, 0, 0 binary is 4, right? 0, 0, 0, 0 is 0, 1, 1, 0, 1, 1, 1, 0, 0. So I just create a value 0x4. 0x4 is nothing but all zeros. So in this pattern, there is only in the bit, if you look at the bitwise representation of 4, if you take all the zeros, there is a 1 only in that position, which is bit 2. Are you understanding? Are you all following me? So there's going to be 1 in only that value. Now, what I will do is I'll do x ampersand m is the mask, and I will just print z. Now, what will be the result? As long as that bit position in x, if that bit position is 1, the result will be non-zero, right? The moment that bit position is say 0, the result of this operation is going to be 0 because everything else in this bit is 0. Is it clear? So the only time x ampersand m will have a non-zero value is when bit 2 in x is non-zero. If that bit position is 0, this result is going to be a 0. Is that clear? So this is, if suppose I'm reading a register from that device, that bit 2 is telling me whether, say, received data is available or not. All I can do is simply create a mask like this and I can put a statement if this and is equal to 0, I know there is no, the register is empty, else copy that value. Are you getting how we program in embedded world? So this is why this bitwise operations are very important in the embedded system, because often you'll be reading a register, you'll be checking 1 bit, 2 bits, you can create any type of mask, but this is just an example. Let's run this and see what it prints now. I didn't define Z, so that was the error. Okay, let's see whether it runs now. So Z is having a non-zero value here. Okay, that's because this nibble here was F. F is what? F is 1 1 1 1, right? Instead of this, if I make this position 0, okay, bit 2 is what I'm asking, right? I make this position 0. 1 0 1 1 in hexadecimal is what? 1 0 1 1 is A is 1 0 1 0, B, right? B is 1 0 1 1. Is that right? I hope I'm right. So let's make, instead of F, let's make it B. Assume, see, this pattern is, I am just simulating something that we are reading from a register. Just as an example, assume we read a register and we got this pattern. I am doing the same operation now. Let's see what is the result. The result is a 0. So as I already told, right, it's very easy to write code and see anything non-zero is true and 0 is false. I could have just said here, I could have written some code here which says, I can just say if z, I can say, print data available, else I will just say data not present or something like that, right? Okay, so if I run this code now, we'll just say data not present. So this is how you will actually, when you implement a device driver or something, you'll be reading a register and you'll be checking something and taking action. So if this was F, my logic will now actually go to the other path, data available, and in real world I might have actually gone and the data itself may be available in other register. I will go and read it. So this is how you typically write device programming. You'll read something, check something, take action. So this is the reason why the bitwise operators are very, very important. And we'll now quickly finish with one more concept in the bitwise. I'll probably stop with that here. So we saw the bitwise and or XOR and NOT. And there's one more interesting thing called bitwise shifting. Like this is also useful sometimes to shift the bit pattern and check certain things, right? So there are two operators. One is called the right shift operator and the left shift operator. There are two operators. One is called the right shift, another is called the left shift. So what it does here is, it does a, like in a shift register that we have seen in hardware, right? Digital logic, we have seen shift registers. It just shifts the bit position, okay? So how does it work? So let's take some, basically, and it takes an argument also. It takes the number of positions to shift. So you can write something like this here. Assume we had a variable called x with a stored. This is a bit pattern in binary 10 10 10 10 10 like this. And I have declared another variable called y, and I write the statement y is equal to x left shifted by 1. What will happen is, this whole bit pattern will be shifted left by 1, and on the rightmost, right, the LSB position, a 0 will be inserted. Okay, so what happens, you can see here, earlier this was bit position 0, now this would have moved to bit position 1, and a 0 will get inserted here. Okay, so the new pattern, as you can see, becomes this. And if you try to read it, it now actually becomes 5554. If you print it in hexadecimal, it will print 5554. What happens is, this pattern is left shifted, so you lose this position. This 1 will be gone doing a left shift, right? So this MSB is lost. The MSB position, which was the bit 15 in this case, is lost, and a 0 will be inserted in the bit position 0, and every other thing will get shifted by 1. Is that clear? So that's called a left shift operation. Similarly, you have a right shift operator. Instead of 1 here, if I had put 2, it will get shifted by 2 positions. So 2 zeros will get inserted. Okay, this is the left shift and right shift. And just a couple of examples here. So this one, if I shift right shift, right? There are right shift, there are two possibilities. Okay, one is called as a logical right shift, another is called as an arithmetic shift. So if you have an unsigned variable, when you shift right, zeros will get inserted in the MSB position. The LSB will be lost. MSB, you will keep inserting zeros. If you do an arithmetic shift, is done when you have a signed variable like short. In that case, that bit position, the MSB bit position will stay as it is. If it was a 0, the MSB will continue to stay a 0. If it was a 1, it will continue to stay 1. Which means, if I right shift, this 0 would have come here also, this 1 would have come here also, but this 1 will not change, or the 0 will not change. That is called arithmetic right shift. That is done to handle things like, there is one more property of shifting. If you shift left, it is actually like multiplying by 2. If you shift right, it is actually dividing by 2. When you're dealing with signed quantities, if you right shift to get if I have -6, if I right shift, I want to get -3. Only when you do something like this, the 2's complement notation will have the right value of -3. So that's why if it is a signed quantity, when you do a right shift, this is called sign extension. We call this a sign extension. So basically the sign position stays the same. And if it is 0, a 0 will move to the other position. If it is a 1, the 1 will come here, but this 1 will also stay. Is that clear? So this is called binary, bitwise shifting. So shifting is also useful in register manipulation. You may sometimes shift something and take a value. For example, you might have a register. For example, you may have a register. Some fields are declared here. Maybe there may be some status flags, status flag 1, status flag 2. And here you may have some 4-bit field which is having a count of something. Okay. Now I'm interested in that count, right? What I can do is say there are bit positions 0, 1, and 2, 3, 4, 5 gives me the count. So what I can do is I could have read this in some register, and I can do a right shift by 2. Right? If I right shift by 2, these 2 are gone. This count is coming into 0, 1, 2, 3 position, right? And then I will do a mask with 0xf. 0xf is what? 1, 1, 1, 1, which means all the upper things, everything else here is lost. I am not worried about it. Only these 4 bits, whatever is there, if I mask it with 1, 1, 1, 1, right? I will just get that value. If it was a 0, 1, 0, 1, if I mask it with 1, 1, 1, 1, I'm just going to get 0, 1, 0. So basically, these 4 bits will come unchanged, but all the upper bits will get 0. Even if it was a 32-bit register, everything else will become 0. So what happens? I actually get that count as a value. So that 16 4-bit value, which may be ranging from say 0 to 50, I now get it in my variable easily. So this is the use of shifting and then masking. Is that clear? So this is how we can do shift and mask. So I'll stop with just showing one example in the online compiler here. So we had this, right? Let's for a moment assume these 2 are our, this 1/4, those 2 positions are actually our count that we are interested in, right? I want to extract it. So what I can do, first I can take this value x. I have to ignore the lowermost 4 bits. So I right shift by 4. Okay, I right shift by 4. Okay, and if I print it, you will see the shifted pattern. But I am now interested in, after right shifting, I'm interested in these 2 nibbles actually, which means there are 8 bits there. So what I can do is I can mask it with the pattern. I already right shifted, so I just mask it with ff, which is like 2 nibbles, and then I print that value. Let's delete all these things, not needed. So all we are doing is, so we have this pattern. Assume we have read this from a register, okay, and we are interested in these bits. Assume there's some count in that register which tells me how many bytes are available in my FIFO or something like that, right? So all I'm doing is, this mask is also not needed here. Let's delete that. All I'm doing is first shifting it. I'm moving these 2 to the lowermost 2 nibbles, right? If I shift it by 4, what happens? This f is gone. F is 4 bits, that will go away. This 1 and 4 will come to the lowermost 8 bits, which is 2 nibbles. So to mask that, I am doing masking with 0xff. 0xff is nothing but 0x000000ff, right? Just to be clear, all the upper bits, all this fi, everything will go away, and I'll only get the count which I'll get here. So let's try running this. Sorry, I didn't mask it. I just assigned it, right? That's a mistake. X and this. So I mask it. So I'm getting this value 4f, which is what I'm interested in. If that 4f was a count, I know I'm getting a count in my variable z, and I can take some decisions based on it. Is that clear? If only 7 bits, assume it was not all 8 bits, right? If it was only say 7 bits is a counter, right? My mask will be different. My mask will be 7f, right? Because only the 7 bits are my counter. If I mask it with 7f, now I'll get a different value. In this case, 4f, it is not changing because this was a different value. If it was, the value was a, so ff, right? Or instead of say, I'll say 1 c, let's say. If it was say cf, the value was say something like cf, right? If I mask it, now you'll see 4f coming. Can you see the difference? So I've ignored, c is actually 1100. So that 1 is gone, uppermost 1 is gone, so it becomes 100. So that's why you get a 4f here. So this is how you deal with embedded programming, right? You'll often read some registers, mask something, shift something. If you see any embedded code, especially if you look at the microcontroller code, you'll see a lot of definitions. You'll see a lot of hash defines with all these masks, which correspond to some bit position of the register. So because the register itself may have some 20 different fields of different width. So there'll be a mask, which is typically the size of the field width. And then there'll be something shift to shift it to the right place to get the value. So you'll have all these macros or hash defines. And if you look at the Renaissance code, if you go and see, for example, if you browse through the header files, right, you'll see a lot of mask and definitions because it's very common operation in the C programming. So as an embedded programmer, it's very important to actually get comfortable with bitwise operations. So hexadecimal notation, bitwise operations, or like, it's like ABCD for an embedded program. So you have to be really comfortable so that you can keep, for processing things quickly and understanding the bit definitions, register definitions. You can quickly write the register definition, what should be the mask definition needed for that, and so on.